Hi, we're going to find the area between two curves. So it's just taking two integrals. What we do is we take the integral of the top curve. So that would be this red one here. So we're going to call that f of x. And if we take the area of the red curve, you get all of this area from the curve down to the x-axis. And so we're going to call that f of x. And then if we take the area underneath the green or this upward concave up parabola, we're going to call that curve g of x. If I take that away, what we're left with is just the area between the two curves. So to find the area between the two curves, we take the integral of the top, what I call the top curve minus the bottom curve. Okay, so we're going to do this in an example. I have the curves y is equal to x squared and y is equal to negative x, or x squared plus 2, sorry, and y is equal to negative x graphed. And we are only going to find the area that is bounded between those two curves, and x is equal to 0 and x is equal to 1. So I am just going to draw that in. And then I have my top parabola curve and my line down here. And we're going to find the area between these two curves. To do this, we take the integral of the top curve minus the bottom curve. And whenever we do top minus bottom, we are taking the integral with respect to x. So we need to know from what our left bound is to our right bound. Okay, so our left bound is x is equal to 0, and our right bound is x is equal to 1. So 0 to 1. Our top curve is x squared plus 2 minus our bottom curve, which is negative x. All right. And then we're taking the integral with respect to x. And then when I do this, I get the area between the two curves. So I'll just put area is equal to. Okay. So let's go ahead and simplify a bit. I get from 0 to 1 of x squared plus x plus 2 dx, and that's just a polynomial, so I'll go ahead and just take the antiderivative, which is 1/3 x cubed plus 1/2 x squared plus 2x, evaluated from 0 to 1. All right, so I get an area is equal to 1/3 times 1 cubed plus 1/2 times 1 squared plus 2 times 1 minus, and then when I plug in the 0, I'm just going to get 0. So I get the area is equal to 17 over 6. And that's that for that one. Let's move on to the next example. All right. So I have this time when the region is between two intersecting graphs. So this time the graphs actually touch, so we can see that they intersect here and here. So we need to find the area between, and I always label them. So I'm like, okay, this is y is equal to 2 minus x squared. And the second is, this is g of x is equal to x. That it's over here. I guess I can just use that. G of x is equal to x. All right. So we are going to figure out what the area between these two curves are. So I know I'm going to have to take the integral of the top curve, which is 2 minus x squared, and subtract out the bottom curve, which is x. And because we're moving from left, since my equations is written in terms of x, we're going to use dx, which means that we need to find our left bound and our right bound. So where do these two curves intersect? Well, you just set them equal to each other. So 2x minus x squared is equal to x. We solve, I'm going to get 0 on one side, so x squared plus x plus 2. So I get 0 is equal to x plus 2 times x minus 1, because this should be a minus. Go ahead and fix that for you. Okay, when I subtract, so then I get x is equal to -2 and x is equal to 1. So when x is equal to 1, the curves intersect, and when x is equal to -2, the curves intersect. So our bounds are from -2 to 1. All right, so we're going to move on here, and the area is equal to the integral from -2 to 1 of, I'm just going to rewrite this as -x² minus x plus 2 dx, and then I get -1/3 x cubed minus 1/2 x² plus 2x, evaluated from -2 to 1. All right, so this time I'm actually going to have to substitute this in twice. So -3 times 1 cubed minus 1/2 times 1 squared plus 2 times 1. Wow, I could have turned on a light, but now this is too late. Okay, anyway, now I'm going to substitute in -1/3, and I'm going to put 2 in for x, so -2 cubed minus 1/2 times -2 squared plus 2 times -2. And what I end up with next is -1/3 minus 1/2 plus 2. I'm going to leave my minus and go ahead and evaluate inside the parentheses first. So I get negative times a negative is a positive, so I get 8/3 minus 4/2, which is 2. Yeah. And then I get -4. Okay. We keep going here, and I get -1/3 minus 1/2 plus 2 minus 8/3 plus 2 plus 4. -1/3 minus 8/3 is -9/3 minus 1/2 plus 8. And this is just -3. So I get 5 minus 1/2, which is 4.5, or 9/2. So the area between the two curves would be 9/2, or 4.5. All right, so the sine curves intersect infinitely many times, bounding, and so each one of these bounding regions here and are equal in value. So we need to find the area of each one of those regions. In other words, we're going to find the area of one of those regions so that we know the area for all the rest of the regions. Okay, so I am going to find the area of this region right here because that seems like the easiest to me. So I need to first figure out where the curves intersect. So I'm going to say that the sine of x, where is the sine of x equal to the cosine of x? And I am just going to divide both sides by cosine x. And so I get 1 is equal to the tangent x. So where is tangent x equal to 1? It's when x, trig, guys. It's when we have pi/4 plus pi n. Okay, so that means that this first intersection will be pi/4, and then we need to add pi, so that gives me 5 pi/4 for the second intersection. So now, which curve is the top? The sine curve in my graph here is the top, and the bottom is the cosine graph. So when I set up my integral, my left bound is pi/4, and then I'm going to find the area all the way up until 5 pi/4. My top curve is sine of x, and my bottom curve is cosine of x with respect to x, so dx. And now we integrate. So the area is equal to negative cosine of x minus the sine of x, evaluated from pi/4 to 5 pi/4. All right, so I subtract the cosine of 5 pi/4 minus the sine of 5 pi/4 minus the negative cosine of pi over 4 minus the sine of pi over 4. Okay, so evaluating, I love this because we're over 4. We end up with root 2 over 2 for everything, except so root 2 over 2, but it's negative, minus root 2 over 2, minus negative root 2 over 2. Remember, 5 pi over 4 is in the third quadrant, so sine and cosine will both be negative. So that means that it's going to be negative root 2 over 2, and then I needed to bring down the negative sign, and then I have negative root 2 over 2, and I needed to bring down the negative sign. Okay, and then I'm going to subtract. Cosine pi over 4 is in the first quadrant, so both the x and the y will be positive, so I end up with just negative root 2 over 2 minus root 2 over 2. All right, looks like I need to simplify. So I get positive root 2 over 2 plus positive root 2 over 2. And then I'm going to distribute, giving me plus positive root 2 over 2 plus positive root 2 over 2. And I just add up all the ones. So I get 4 root 2 over 2, which is equal to root 2 times the square root of 2. All right, a couple more examples, and these are a little different. Same idea, but a little different, okay? So what happens when the curve, when the top curve changes? So if you notice, to start, the red curve is the top curve, and then when x is equal to 0, it becomes the bottom curve. So when this happens, you have to set up two integrals. So I always label out my curves. I have, this is f of x or y is equal to 3x cubed minus x squared minus 10x. And then the purple curve is negative x squared plus 2, since it's the parabola, and one is the cube function. So when the graph is between x equals negative 2 and x equals 0, the cube function is the top function, and then the parabola is the bottom function. So I am going to write this as the area is equal to, from negative 2 to 0, the top function is the cube. So we do 3x cubed minus x squared minus 10x minus the bottom function, which is negative x squared plus 2, and we're talking with respect to x, so dx. Then, when x is equal to 0 to x is equal to 2, we're going to add the next area from 0 to 2. The top function is negative x squared plus 2 minus the bottom function, which is 3x squared minus x squared plus 10x. I think we'll move this over. Let's try that again. Okay. Dx. All right, so let's simplify. I get the area is equal to, from the integral from negative 0 to 2 of 3x squared, and then it looks like the x squareds cancel, so I get minus 12x, since I'm going to distribute the negative, dx, plus the second part, from 0 to 2, the integral from 0 to 2, oh, I see where that little 2, there we go. Okay, and then I get negative 3x cubed. So I get negative 3x cubed. The x squareds cancel. And then when I distribute in the negative, I get plus 12x dx. Okay, and then I go ahead and integrate. And it's just a little bit of work. So I get, oh, and this isn't 3x cubed. I made that same mistake on my paper, but you know. Okay, here we go. So I get 3 over 4x to the fourth minus 12 over 2x squared. evaluated from -2 to 0, plus 3 over 4x to the fourth, but it's negative, plus 12 over 2x squared, evaluated from 0 to 2. And then we start substituting. Get 3/4 times 0. Okay, so when I plug in 0, I'm going to get 0. So I'm just going to put 0. And then we're going to subtract out 3/4 times -2 to the fourth minus 6 times -2 squared plus -3 over 4. Be really careful of all your parentheses. Times 2 to the fourth plus 6 times 2 squared. And then again, when I plug in 0, I'm just going to get 0, so I'll just subtract 0. Okay. And I end up with, looks like 3/4 times -2 to the fourth would be -12 when I substitute in the negative, or when I distribute the negative. And then I get -24 times -1 is +24. Okay. And then here I get -12, so plus -12 plus 24. All right, and then when I add those all together, I get an area of 24. That's it. So when the curves switch location, so when the top curve becomes the bottom or the bottom becomes the top, then you have to make more than one integration. All right, last example. These are fun. So what happens if okay, so we can still, actually, let's just do this. The function is written in terms of y. So we use y instead of x. So instead of taking the top function minus the bottom function, what we're going to end up doing is taking the integral of the right function, the right curve, minus the left curve, and with respect to y, dy. And I use c and d for the bounds, just so we don't get them confused. Okay, so if we look at our function, we have f of y is equal to 3 minus y squared. So this function here is 3 minus y squared, and the line is y plus 1. So I want to find the area between these two curves. So I look for, and the reason why I want to do this in terms of y instead of in terms of x is that if I try and get the area between the two curves vertically, what happens is I end up with a problem here because the top curve and the bottom curve are basically the same curve. We can do this, but it's just more work. And another thing I noticed is that the top curve switches. So first it started as the line, and then it switches to the what would be the square root. Okay. So instead, what we're going to do is take the area between the two curves going horizontally. So we're going to take the right curve, and notice that the parabola is always the right curve, and then the line is always the left curve. So I'm going to take the integral from c to d of the right minus the left dy. Okay, so we'll set that up. The right is 3 minus y squared. The left is y plus 1, and all of that with respect to y. Now to get the bounds, instead of the bounds being from left to right, now we take the lowest part of the area up to where you want to find the highest part of the area. So from -2 to +1. All right, and now we integrate. So or now we simplify. The area is equal to the integral from -2 to 1 of negative y squared minus y plus 2 dy. So we get negative 1/3 y cubed minus 1/2 y squared plus 2y, evaluated from -2 to 1. Then we plug in negative 1/3 times 1 cubed minus 1/2 times 1 squared plus 2 times 1, and then subtracting out negative 1/3 times -2 cubed minus 1/2 times -2 squared plus 2 times -2. I have to be so careful. All right. And we get negative 1/3 minus 1/2 plus 2 minus 8/3 minus 2 minus 4. Okay. And I end up with 4.5. And that is it for today. Yeah, we end up with 4.5 because this is the same, basically the same problem we did earlier, just written in terms of y. So if you notice, like the graph of this second one we did is really the same graph. It's just written in terms of x instead of y. That's fun. Okay, I'll turn on the light for the second video. Bye!